This is the first of 2 lectures for today, and in this one we're going to look at the interior of the atom, and this is all material from 7.1, just some basic background information. We've talked about this a couple times, but here is the specific teaching for this. So, the interior of the atom is made up of a few different things. The nucleus is protons and neutrons, and they're always a bit conflicted. They're always not wanting to get along, but they need each other in order to be stable. So let's figure out what is causing all of this. And I made this for our class time, so these questions won't be worried about during this video. All right, so where did protons and neutrons come from to begin with? They came from some place called the Big Bang. Before the Big Bang happened, there was all of the energy in the universe was in a tiny, small place, and it was so much energy, the temperature was too high, and matter could not be formed. So then expansion started for some reason, and that expansion is called the Big Bang. And during this very first period of inflation, the temperature of the universe, the energy of the universe spread out really fast, and that temperature dropped. So because that temperature decreased due to the spreading out of energy, there was the universe was now cool enough that matter could form. It wasn't converted back into energy immediately. So what happened? Well, the first things that happened were these protons and neutrons were formed. The whole universe was made up of protons, neutrons, electrons, and then the antiparticles of these particles. So antiprotons, positrons, antineutrons. And they spend a long time just colliding and disintegrating each other, going from being matter to being not matter, back into energy due to their collisions with their antiparticles. But in the end, we ended up with all of this matter, not antimatter. Nobody has a real good explanation why that happened. And in this afterglow pattern, then we had all of the particles that exist started after that section. Then the rest of this is just the reorganization of those particles. And so during the Dark Ages, you had protons and neutrons floating around. Hydrogen was being formed. That's a proton. You're getting some helium being formed, where these two would come together and form deuterium first, then tritium, then finally helium. Electrons are there, so they're becoming full atoms. And then at the end of the Dark Ages, those atoms start to collect as big giant stars. And as they start to condense, that temperature goes up due to gravity. So gravity is attracting those molecules together, those atoms together. And the closer they get, the more they bounce off of each other, the more you start to concentrate energy. And that's what's happening in the rest of this, is energy becomes concentrated in stars. And then fusion is kicked off. So protons get smashed into protons, you get helium made, then you start building the bigger and bigger and bigger elements. And the light starts shining at the end of the Dark Ages. And that's when our first stars turned on. So these guys have been around forever, and they are constantly being interacted with. But as the universe spreads out and spreads out, those nuclear interactions of fusion become less and less, because we formed more and more big pieces of matter as you get down here closer to present time. So that's where they were trying to figure out who they were, what they are, where they are, and how they're going to interact. First, they started off all alone. Then they paired up a little bit due to their collisions and then the strong nuclear force holding them together. And protons were trying to push each other away, but they attracted electrons, and there was a whole bunch of stuff going on, which we'll learn more about in just a second. So, what is a proton and what is a neutron? Protons and neutrons are not fundamental particles. They're made up of smaller things called quarks. Protons are 2 up quarks and 1 down quark, and neutrons are 2 down quarks and 1 up quark. And so the only thing that's different about them is one has an extra up quark, and the other one has an extra down quark. We're going to learn more about those quarks in 7.3, but these two things are what's happening on the inside. So protons and neutrons are not fundamental. They can be broken down, and the nature of these quarks are what make the difference between a proton and a neutron. A neutron is slightly heavier. A proton has a positive charge, and those charges come from the from the quarks that make them up. So here we go. We've got proton. And basic things you need to know: positively charged, and the most important thing on the planet, and actually the universe, because all the elements are determined by the number of protons. And yes, things are attracted to them. Electrons are attracted to him. All the little things love me. Those are the electrons that love him. But they can never have me because, they can't come that close. Sphere of influence, that's the atom itself and the region that positive charge will affect. Then you have neutrons, and neutrons are like proton's sibling. Always keep it from making a mess of everything, so you can think about this as like the bodyguard or the protector or the stabilizer or the counselor or whatever you want to do. However you want to visualize that, that's the job of the neutron. It's to help hold those protons together, if you want to think about it as having a job. And it does carry mass. So that's the other important piece of the neutron. Protons and neutrons together give the atom 99.9% of its mass. So those forces I was talking about, we've mentioned these in class. We're going to be focusing on the strong interaction today, and that's what is attracting neutrons and protons and neutrons and neutrons and protons and protons. And then we're going to talk about the electromagnetic repulsion, because those are the things that push away. Protons are trying to push away from protons, but they don't interact with neutrons in that way. So neutron is the cool friend that isn't affected by that proton's positive charge. So there's that battle going on inside. Protons have electromagnetism and strong interaction, and they also have gravity because they have mass. Neutrons just have strong interaction and gravity. The weak interaction is happening inside of both of these, but that's going to be more of a 7.3 topic as well. All right. Here's just another breakdown of that. I would spend some time reading through this and getting to know the range, and then this is all going to be 7.3, what the particles are going to be. But the strength and the range are very important things to know. Be able to organize them by strength, be able to organize them by range. That's a very common IB style question. And here is the conflict that protons are trying to push away and neutrons are trying to hold things together. Protons also carry that strong nuclear force, so they're attracting neutrons and they're attracting other protons. So they're attracting each other, but we need that electrostatic repulsion as well in order to stabilize the nucleus. Without that repulsion, then the strong force would destroy itself. It would reduce these things smaller and smaller and smaller. Yes, because of binding energy and mass defect. So that's 7.2. We can talk more about that at 7.2. But this is the fundamental conflict inside of atoms themselves. Most atoms have figured this out, and they have turned into stable nuclei because they've already done beta and gamma decay and alpha decay. Too many protons, it's unstable. Why do you think that is? Take a moment, think about that. You need to be able to answer that question. Too many neutrons, unstable nucleus. Why do you think that is? Take a moment, think about that. You need to be able to answer that question as well. All right, the ration, that's supposed to say ratio. There's no perfect ratio of protons to neutrons in an atom. It starts off perfect at 1:1, but then you need more and more neutrons per proton as the atom gets bigger and bigger. And if you can see, so this black line right here is the region of stability, and you see it's a very thin line. There's not too many stable atoms out there, stable combinations of protons and neutrons. There's a ton of stable atoms. 99% of all atoms would fall on this black line. But if you're an isotope that happens to have too many neutrons for that number of protons, you will go through beta minus decay, trying to turn beta minus, yes. You've got too many protons for a number of neutrons. Beta minus turns neutrons into protons. Beta plus works the other way, and that goal is to get it back to that black line. If you're a big atom up here, then you do alpha decay, where you're kicking out large particles, and in order to get the proper number to become stable back down here on this black line. So as you get bigger, you need more neutrons for every proton. Why would this break down for bigger elements? Once again, that's going to be a question you need to be able to answer. For the first 20 or so, you can see here that it is about a 1-to-1. So 20 protons, but a mass of 10 protons, but a mass of 20, so that's 10 and 10. 2 protons and a mass of 4, so that's 2 and 2. 9 protons and a mass of 18.9, that would round to 19. 9 to 10, that's okay. 8 to 16, 8 and 8. So that pattern holds true for most of the small elements. As you get bigger, some of these down here, you can start to see that pattern breaks down once again. Down here at the bottom of the periodic table, this is from the bottom 2 rows, 101 to 258. There's about 50 more neutrons than there are protons. And why is that? In order to make it stable. Yeah. So what happens when atoms are unstable? That's when they go through their decay processes. And you've watched other videos on how those decay, alpha, beta, gamma. And the purpose of that is to get it to its lowest energy state or most stable position. And you've already explored that mechanism. Now this is just going back and looking at why does that happen. All right, a brief recap. What is this all about? The atom is made up of protons and neutrons. We don't care about the electrons for particle physics. They do a little bit for us, and we're going to learn more about that in our next video. But protons and neutrons are what make the atom stable. The electrons are just like the dressing on the outside that make atoms interact with other atoms. So those two things are the defining most important pieces to an atom. And protons are trying to repel protons due to that electrostatic repulsion. But protons and neutrons both have the strong nuclear force and attract each other with that. And you need a balance between those two in order to have a stable nucleus. And I think that is all we need to know about the inside of an atom. Yeah, so like I said, be able to answer these questions, understand this graph, where beta minus, beta plus happens, when you have too many neutrons, what happens, when you have too many protons, what happens, and this relationship between strong nuclear force and electrostatic repulsion. All right, have a good day. See you in the next video.